So today we are going to start the LR circuit.
Okay.
So the role of L in let's say circuit is similar to the role of mass in mechanics. Both represents inertia. So everything which is related to mass, you can always keep a create a correlation or similarity, or you can say analogy in L as well. So for example, the role of L and role of M is so similar that the formula will also resemble here and there. So first of all, the L is representing the inertial character of a circuit, and because it is representing inertia, so we know that inertia having the quality to resist the change. Okay. So what kind of change we talk about in mechanics? When we say change, we talk about the motion, okay? And we talk about particularly velocity. So velocity represents the state of motion. So one value of velocity represents one particular state of motion. The other velocity will represent the other state of motion. So we say that the state is constant, it means we say the velocity is constant. And we say that acceleration is a factor which will affect the state of motion, hence will change the velocity. So why this analogy is important, that many times uh, knowing one theory is sufficient to recall the other theory. So let's say in the examination, if you tend to forget certain things, this analogy will help you in recalling the formula and the behavior and various other things, which we will also see. So both represents inertia. Now, in case of mass, it will resist the change of velocity. Like if a mass is at rest, if you try to move it, it will try to oppose you. So just like inertia can have two types, inertia of rest and inertia of motion. Inductor will also have these two inertia. So when there is a velocity, we say inertia of motion. And when there is no velocity, when you are at rest, we say inertia of rest. So a same mass can have two types of inertia, inertia of rest, which we only measure in terms of mass, and inertia of motion, which we measure in terms of mass into velocity. So this represents the inertia of rest, and this represents the inertia of motion. So what we call this as momentum, right? So if you want to understand the inertia of rest, just mass is sufficient. Similarly, in a circuit, if there is no current, it is like a rest. So L will oppose the change from 0 to any value. Let's say if there is no current in a circuit, the L will be very happy. Okay, there is no current. It's the inertia of rest. If you try to establish current, L will oppose. So where I is 0, it is equivalent of inertia of rest. And then we have L into I, just like mass into velocity. So you can understand that the role of current is like a velocity. You can also correlate that current is like motion. So Li is like a momentum of electrical circuit. It's a inertia of motion equivalent. So you can think this way. So in circuit theory later on I'll teach you that this is called flux. I think I have explained this, right? The
Yes.
phi equation.
Yes.
So this is the like a self flux linked with the loop itself. So flux is like a momentum in a circuit. So these rows are very much one-to-one relation. You can always correlate. So you can think of momentum, you can think of flux. So if we talk about the conservation laws, like conservation of momentum, here we talk about conservation of flux. So here we follow the conservation of momentum. So here we talk about the conservation of flux. So this one-to-one relation is very much prevalent and it is everywhere. So the world of electrical circuit, we have always correlation with the mechanics. And in fact, many times we can derive the formula from one concept into from mechanics into electrodynamics and vice versa, depending upon what you remember. Okay? So if you remember the electrodynamics formula, you can derive the mechanics and vice versa. Now, just like mass, you can see in a moving state, but in a circuit, nothing is in motion, physical motion. So there we have to only understand. So a current is like the motion equivalent. Okay. So current will represent the velocity. So I'll just mention here. So electric current is velocity equivalent, and velocity is defined as rate of change of displacement, right? So electric current by definition is dq by dt. So you can again correlate that the role of q is similar to the displacement, right? So q
Yes.
is equivalent of displacement. And not only this, you can in fact correlate a lot of more things. Let's say you talk about the kinetic energy, half mv square. So an inductor will also have energy, which we call the energy stored in the inductor. And if you go by the correlation, the way of writing is very much similar. You write half, the m should be replaced by l,
F by L
and
and
v.
V by I.
And in fact, this is the formula which will come across in inductor. It's half Li square. So a current, if a current I is flowing through an inductor, it is storing this much energy at that moment. So any inductor carrying current I will store this much energy.
Yes.
So similarly, we can correlate everything else. So let me show you some more correlation, which is very interesting. So you can correlate like force. So force dynamics. So in mechanics, if we talk about force, here we talk about the EMF, the electromotive force. So the role of force and electromotive force are very much similar. Let's try to understand the role of resistance. The resistance represents the drag coefficient. So if you have heard about the drag force, so drag force is the force which happens due to the velocity, and by value it is B into V. So the B, if you write the force as BV, then B represents R. R is equal to B. Both are like a resistance, the drag
Yes.
coefficient, right?
Yes,
So
sir.
the BV here becomes so the drag force equivalent, the you can say drag EMF, we can write equivalent as IR, because BV, the B is R and V is I, right?
Yes, sir.
which is very much like Ohm's law, right? Then you can correlate things like spring force. Half kx square. And if you remember, the x square is called charge. X is like displacement is like charge. So q square 2 and
Yes.
k becomes 1 by c. So this is the energy stored in capacitor. So you can also understand that the role of c is equivalent of 1 by k. So inverse of spring constant is like capacitance of a circuit.
Sir, how is that correlation made?
Yeah, you can think this way. So if you deform a spring, what will happen? It will store energy. So if you give charge to plate of capacitor, it will store energy, right?
Yes, sir.
And also capacity C means capacity to store charge. Like C is like how big the container is, right?
Yes, sir.
So C represents the ease of storing. Like bigger C means more
More.
charge can be stored, but bigger K is not the same. Bigger K means difficult to deform. If
Yes, sir.
K will grow, then it is more difficult to deform, right?
Yes, sir.
So it's inverse relation, right? You can understand.
Yes, sir.
So here we have inverse relation.
Okay, sir.
Okay. Anything else you can think of from mechanics to here? Potential energy, kinetic energy. Okay. Fine. So let's move towards the LR circuit.
Sir, heat and friction.
Yeah. So friction will come under the drag force, like mu into L.
Yes.
Something like this.
Yes.
So now what we're going to learn here is you can think, let's say there is a bulb. And this bulb is connected across a coil with large number of turns. The coil will have the self-inductance L, and there is just like a cell attached here with a switch. So bulb is like a resistor. Okay. Now, in the absence of this inductor, we can say that the inertia of circuit is almost negligible. It is just like a massless object, not exactly zero mass, but almost negligible mass. Okay.
Yes.
So
Sir,
in case of
able to hear me?
yeah, I can hear. So in case of in the absence of L, the moment you switch on, the bulb will glow to its maximum value in no time. Okay.
Yes.
So the bulb will glow to its maximum limitation, maximum power, whatever is written there. But the role of L is to slow down the process. So L is like inertia, so it's difficult to change the current from zero to its maximum value in no time. Rather, it will take some time now. So bigger the value of L, the more time it will take to achieve the maximum value of current in a circuit. See, the role of L is nothing. L will just slow down the process. But
Okay, sir.
sometimes it is desirable. Sometimes we need to control. So generally what we do is we put an inductor so that if a device is very sensitive, there is a chance of damage if there is a sudden increase of current. But for such a sensitive device, uh, inductor in the series will prevent the sudden change and hence will prevent the device from the damage. So sometimes it is a desirable effect that we want to have in a circuit, because eventually the current will go to the value which it is supposed to be, but the change will not be impulsive, change will not be quick, rather it will be a delayed event, which is good. Okay. So this kind of circuit, what will happen? So this circuit will try to establish current across a resistor. So now the value is 0. So if you talk about the inertia of rest in this circuit, L is at rest. You can think it this way. If there is no current, L is at rest. So the moment you apply the force, what will be the velocity of the L? 0 itself. At the moment of applying force, the momentum will take some time to change, right? Right now you have 0 momentum. So from 0 to next value will take some time, right?
Yes, sir. And T is equal to 0.
Yeah. So at t equals to 0, we write 0 plus just after closing the switch. If you close the switch, what will happen?
Sir, initially the current will be 0 because of the presence of the inductor, and then slowly it will increase.
Very good. That's right. So inductor will not let the current to establish itself. It will remain 0, and because there is no current, the bulb will not glow at the beginning. So although current is 0, but it does not mean that the di by dt is 0. Di by dt is non-zero. Why?
Yes.
Because current is going to change. So at the very next instant, we will have some current. So di by dt is non-zero, and therefore an inductor will always oppose the change. So because the current is trying to establish itself, it will act as an opposing EMF of value L di by d. So we can say that at t tends to 0 plus, if you write the KVL, so we can write E equals to L di by dt, right? And because
Yes.
E, because this is the only law, right? We can write plus E minus L di by dt equals to 0. The resistance is nothing, right? IR is not there, right? There is no I.
Yes, sir.
So this also gives a very nice value, I mean, a formula that L we can rewrite as so L is defined as the EMF applied upon di by dt at t tends to 0 plus. So in the examination, they will give you that at t equals to 0 plus, the current is changing at a rate of 2 ampere per second, or maybe 0.2 ampere per second. And if the applied EMF is 5 volt, find the self-inductance of the loop or the inductor. So that question can be asked. So L
Okay.
equals to E di by dt at t equals to 0. So this is a nice formula. Or you can say the di by dt value at t tends to 0 plus is E by L. So if you want to know the rate of change of current, it is simply the ratio of E upon L. And this is like you're writing acceleration from a equals to A by A. It's so easy to remember, right?
Yes, sir.
Because if I is the velocity, so d by dt must be an acceleration, right?
Yes, sir.
So again, it is so easy that okay, someone is asking you the question that okay, find the acceleration at t equals to 0. You know the Newton's laws of motion, you can write A equals to A by A. In case if you forget the formula, this is a simple way to recall or remember. That's why I said knowing the mechanical equivalent is a good idea in this chapter. So you will see a lot of similarities, and with the help of similarities, we can actually deduce a variety of relation with ease. So what do we say? Because at t equals to 0, inductor is not allowing any current to flow through it. You can say it is behaving as an open circuit, isn't it? Because only in open circuit we don't have current. Do you realize this what I'm saying?
Yes, sir.
So as a note, we must write here at so after this we will talk about the situation when a long time has elapsed. So when t tends to infinity, so technically we call after long time. So we believe that after long time the current has reached the value it is supposed to.
Sir, steady current?
Yeah. So this is called the steady state.
Okay, sir.
Now inductor will play no role. Now it is as good as a wire. Because inductor will only oppose the change, but once you have achieved the value, or let's say I not the fun value, the di by dt is not going to change. There is no acceleration. So in a way, the state we are not trying to change. So we are not trying to change the state. Therefore, we cannot expect any resistance from the inductor, and therefore, this is as good as a plain wire. So it seems like we just have a resistor and an EMF source, and therefore finding I naught is even easier. We can just write E by R. So as a note, what we can write at so at t tends to infinity,
Yes,
an
sir.
inductor will act as short circuit.
Simple wire.
Yeah,
Yes.
it's called short circuit in the language of circuit theory. So you can replace by a wire and solve the circuit. So based on these two extreme cases, we can solve a variety of problems. So let me give you one example. So we have to register. So can you find the current through the cell just after switching, closing the switch, and after a very long time closing the switch? What will be the value of I? And I is the current through the cell.
So E by R2 for t tends to 0.
Yes, right. So for t tends to 0, it is E by R.
Yes, sir. And for t tends to infinity, E by R equivalent. Yes,
This one's right.
yes, sir.
Very good. So dealing with the extreme case is very easy. We just need to know the behavior of inductor. So what really we are interested in is the duration in between, and that is called transient state analysis. So what is transient state? When the current is trying to grow its value to its fullest value. So d-ability is always non-zero. So when the d-ability is non-zero, we call transient state.
Yes,
Except the zero and the infinity, what is called the anything in between. Okay. So you switch on, that is slightly more than zero. So that is the beginning of transient state. Up to the steady state is called transient state, and in that state, current will vary with time. So the circuit so we have already switched on the circuit. Some time has elapsed. So at any instant, let's say current is I, and also you can assume d-ability is positive, means it is trying to grow. So what will be the KVL?
minus L di by dt minus IR is equal to 0.
Excellent. You can see it is a differential equation in I because the d-ability is right there, right?
Yes, sir.
So can you solve this?
Yes, sir.
Good.
sir?
Yes.
Sir, I'm getting E by ln of E by E minus IR is equal to R by LT.
Yeah, something like that is correct. So you are getting something like this question, right?
Yes, sir.
So I turns out to be E by R something like this, right?
Yes, sir.
So if you want to, you can completely draw the mechanical equivalent of this question. I'll tell you how. So imagine just
Sir, can you just come back in a minute? Sir, are you there?
Hello, Sikaru there.
Sir,
Hello.
yes, sir.
Sorry. I got it. So mechanical equivalent problem is, let's say we have a mass and you are applying a force F, and there is a air resistance. Now air resistance will create a drag force. Let's call the drag force as B. So if I want to derive the formula of velocity as a time function, what I can write is, so you can see E by R. What is E? Force. R is B.
Yes, sir.
1 minus E bar minus R E by. Can you see this?
Yes, sir.
So you can see it's a very much similar to a problem. Like say if you want to find the velocity of a body moving, having the force F applied to it, and the drag force is proportional to velocity. In that case, you can add this answer directly if you know this one, or vice versa.
Yes, sir.
I can show you another problem. Let's say so we are ignoring the buoyancy force, or maybe you can take buoyancy. So if I assume the drag force is again BV and the gravity as mg, and if I release from rest at t equals to 0, then velocity of the particle at any instant will be force upon rest E by R.
Yes, sir.
So it is very powerful. LR circuit is everywhere,
Yes, sir.
and we can correlate things like this. So it's good to know the correlation, and it is very helpful in solving questions.
Yes, sir.
Just so my entire nose is like kind of blocked. I can't breathe from my nose. Anyway,
So, will you be able to continue or?
so I'll continue for some time. I'll speak slowly. That's it.
Okay, sir.
So let's talk about graph. So if you plot the graph, so eventually the current will reach the maximum value I know, and it will grow like this. This will be the asymptote. If you draw tangent at t equals to 0, so what is the geometrical meaning of tan theta? Is tangent
Sir,
to the curve?
the rate at which the current is changing with respect to time remains constant.
Yeah, at t equals to 0.
Yes.
And if that rate remains constant, it will reach the maximum value I naught in a time t equals to tau. And this tau we write as L by R, called time constant. So you can define in a similar fashion as you define in capacitor. But in reality, you can see after one time constant, we can achieve only this much. And this value is roughly 63% of the maximum, which is evident from the formula. So I equals to I naught upon my son by, and we know that this we have discussed in capacitor also. So I hope you can remember.
Yes.
So that is why we write roughly 63%. It is not exact 63. So after one time constant, the current in the circuit becomes this much. So after LR, we can go to the, this was the growth of current we are discussing here. Uh, now imagine imagine we have a circuit like this. So what you can see here, in the very beginning, it is a normal or regular LR circuit. So in the steady state, the current must be E by R, right?
Yes.
The moment you shift the switch from 1 to 2, the left circuit will be broken and we are left with only the circuit, right? So essentially what we
Yes.
have is, so it is again a LR circuit but without a battery or a source. But as I said, let's say if you are driving a car and you stop accelerating, the car will eventually slow down due to the air drag and will come to rest after traveling long distance. But just because you have stopped accelerating, it doesn't mean the car will come to rest. Similar to the situation, if the current in the inductor was I, so at t tends to 0, but that's called the current as I naught. So even though you will shift at that instant, the current in the circuit remains I naught. That's very interesting. So current will
Yes.
not go up. It's just like momentum is conserved at that instant. So it is still MV naught. But because
Yes.
of the air resistance, it will slow down and eventually it will come to rest, current becomes 0. So to solve this decay circuit, you can draw like this. You can see there is no cell here. So you can hypothetically assume a ghost cell. And it's like there is some virtual source giving the current I. And also we can assume GEAVT as positive. It's totally up to you. You can choose negative or positive. So because current is trying to grow in value, so this will approach, right?
Yes.
Right, KB?
So, but isn't the inductor at the moment like trying to maintain the current as it is?
But the air drag is there, na resistance.
Yes, sir. So
So
directly, like, won't it be?
it will dissipate the energy. Na? It's like you have kinetic energy half in V square, but your energy is taken away by the resistor. So you will slow
Yes, sir.
down. So
Yes, sir.
slowing down here means current will decrease.
Yes, sir. So LDI by dt is equal to IR. It's minus air. Yes, sir.
So you can see that if you remove the force, this will be the equation.
Yes, sir. Sir,
Yeah.
sir, why are we assuming that di by dt is positive?
Just to assume the battery polarity.
Okay, sir.
If you assume negative, what will do? You reverse the polarity, you will at minus L diameter, right?
Sir, yes, sir.
Because if you assume diameter is negative, so the minus will become positive. Your
Yes, sir.
final equation is same. You can check.
Yes, sir.
It is just a good idea or maybe a kind of practice which is convenient for anyone.
Okay, sir.
So in the decay circuit, so now because you are starting from the I naught, you're going downwards, so you will decay by 63%. And because we represent the value from the origin, so it is left 37%.
Okay, sir.
It is just like if you are if you throw an object into a medium with air resistance, ignoring the gravity, the air resistance itself will slow it down, right?
Yes, sir.
So maybe you can think of some floating object on a water, right? Or you can think of a block is given a velocity v naught on a rough inclined surface where the coefficient of friction is function of velocity. Think this way. Not function, it's proportional to velocity.
Yes, sir.
Or you can say whatever. You can create some equivalent. So it will slow down eventually, right?
Yes, sir.
And in such case, the velocity will be like this. Okay.
Yes, sir.
So this is the LR circuit. The growth and the decay. Now we'll see something more complex. We should go for So R1, R2L. The question is the moment you switch on, find the current through inductors. So first you solve by the basic, then I'll give you the trick similar to the RC circuit, the Thevenin's method. So as of now, can you solve by the basic KVL, KCL and all?
Yes, sir.
So find I as a function of that. Try this out, then I hit. You solve, I'm coming after 5 minutes, okay?
Okay, sir.
Done?
Sir, still doing so.
Shall I help?
Sir, I was actually confused about bringing the equation in terms of I itself.
Yeah, I'll tell you.
So now I got it a bit. Sir.
We've done something similar to this also, right? Capacity.
Yes, sir. RC circuit.
Yeah. So here the current will be I. You can say I2 or I1. So write KVL here and here. So look one, look two. So I write in the one. E minus IR1 minus I2 RC. This is 0. And KVL in loop 2 is okay. You can always think of the current as growing value. It's L di1 by dt plus I2 R. Now the differential equation is in I1, so I must express everything in terms of I1. Then only we can solve. So what we know
Yes.
is E minus I current is I1 plus I2. So we got I2. Right? This is the
Yes.
whole idea. Now we can solve this question. We need to understand what is the differential equation. Then we can solve.
Yes. Sir. So, but like, should we bring the differential equation in terms of I or I1?
I1 because current through the inductor we are searching, right?
Okay. Sir.
I need to mention.
Sir, the end.
So rest is obvious. Okay. This is the answer.
Yes.
So in steady state, what will happen? In the steady state, the L becomes the pure wire.
Yes.
So all current will go from inductor, and R2 becomes like you're short circuiting the R2, right? Nothing will go from R2.
Yes.
So if you look carefully, this term is the final current through the you can bypass the R2. R2 will get nothing. Okay.
Yes.
So current through the inductor will be E by R1, right? Finally,
Yes.
that is the answer. And you can do by the Thevenin method if you remember. You can solve in one line.
Yes.
Just remove the inductor first. So once you remove the inductor, what is the R electrical? What is R equal? So we short circuit the energy source and we find the R equivalent, right?
Yes, sir.
This
R1
12 parallel
R2 by R1 plus.
we call Thevenin one. And the voltage across AB will be, you can think of voltage divider rule. Because these two are in series, right?
Yes.
So you can find current into R2 plus E by R1 plus R2 into R2 plus. So you can think of RTH, VTH. And now this is the question that we have solved so far called the typical LR circuit. And we know the answer, it is E by R minus R E by plus. So you can substitute VTH by RTH. You get the answer. This is good.
Yes, sir.
Okay, so we can stop today here. We'll discuss a lot about this in the next lecture.
Okay, sir.
So now I'll not keep any lecture for this week till Diwali. So all lectures I'll keep after Diwali.
Okay, sir. Sir, Diwali means till which date, sir?
24th.
24th, sir. Okay, sir.
Because it's my home renovations.
Yes, sir.